Hey, everybody. Let's wrap up 11.3. We're looking at orthogonal projections. Let's jump into it. In previous section in dot product, we looked at the unit vectors E1 and E2. That's the decomposition of the vector V into two orthogonal vectors, unit vectors. These are referred to as the orthogonal projections of V. And so when we do a projection of V onto EK, the notation is that we say proj and then EK subscript and then V. What you're projecting onto does not need to be an orthogonal vector or a unit vector. In this case, I had it as a unit vector. But if we look at the picture, I've got vector V, we've got its two orthogonal components, these two vectors, and when we find the unit vectors of them, I've got E1 going vertical, E2 going to the right. That was just because I had already written out these two lines and make the arrows pointing easier. The projection of V onto E1 is like, you kind of like take this line and slap it down there. Like, what's happening in that process? Well, that is V dot E1 times the magnitude of E1. And the projection of V onto E2 is we're going to dot the two vectors and then multiply it by the unit vector. So this is what we just did. This was our K1 E1 and K2 E2. We just did this in the previous section. But now we can write V as the sum of two projections. The projection of V onto E1 and the projection of V onto E2. Okay. So if we want to find the orthogonal projection of V onto B, we need to normalize B to find the E. So E hat is B over B. And our equation changed from, we have B dot E1 and E1. Well, that's our E. We're substituting in B over B hat. So B over, or not B hat, vector B over the norm of B on the inside times the vector B over the norm of B on the outside. That is the projection of B onto B, where B is any vector there, not just a unit vector. Now, this is a scalar, this is a scalar, B dot B is a scalar. So we can rearrange that to put V dot B over the norm of B squared. This whole thing is a scalar, and we'll dot it by B, or not dot it by D, we'll multiply this scalar times B. And then we've got the projection of V onto B, and we didn't need to stop and find a middleman E. So this is the projection of V onto B. Either of these forms works. They're the same thing. Let's take a look at it. What's going on pictorially? I've got V here and I've got B there. We're projecting V onto B. The projection of B onto B is this right here. And then a vector that's orthogonal to that one would be that one. So this is the orthogonal vector to B. And if I want to find out what that is in terms of V and B, I can just move this up right there. And we can see that if this is V, this is the projection of B onto B, then the orthogonal vector is the end one minus the other one, V minus the projection of B, or V onto B. Or another way of writing that is V minus, this is substituting in projection. So this is the orthogonal vector right there. Okay. Let's take a look at an example. We are going to find the vector projection of V in 3 dimensions. It's 1, 1, 2. We are going to project it onto -2, 3, 1. And we're going to find that that vector projection and a vector orthogonal to B. So let's just jump right into it. We've got the projection of B onto B. I rewrote the formula. We've got B dotted with B over the norm of B squared times B. And that is just plug and chug, right? Plug and chug. 112 times negative 231. I've got 1 times negative 2 is negative 2. 1 times 3 is 3. 2 times 1 is 2. And the norm of B squared is the distance formula without the square roots. So negative 2 squared, 3 squared, and 1 squared is 4, 9, and 1. If we add these up, on top we get 3, on the bottom we get 14. So it's 3/14 times B. The projection of V onto B is negative 6 over 14, 9 over 14, and 3 over 14. Okay. One second. So if we look at the orthogonal vector, remember it was V minus the projection of B onto B. So if I do the subtraction there, 112 minus 6 over 14, 9 over 14, 3 over 14. We get the orthogonal component is 20 over 14, 5 over 14, and 25 over 14. I encourage you to check it, pause the video and check it, make sure those are orthogonal. And we can do that real quick ourselves together. Once you've tried it yourself, is the projection of V onto B orthogonal to this value right here? Let's find out. So we've got the dot product of these, B and dotted with B ortho, should equal 0. So I've got B is negative 2, 3, 1. That should work as well. 2, 3, 1 dotted with the 20 over 14, 5 over 14, 25 over 14. I get 14 in the denominator for all of them. Negative 2 times 20 is negative 40. 3 times 5 is 15. And 1 times 25 is 25. This adds up to 0. I could have done the projection, dotted the projection. I know I was said I wanted this all written out ahead of time, and I did not do it here. But this is what happens when you add stuff to the video that you weren't intending. 14 squared is 196. Negative 6 times 20 is negative 120. 9 times 5 is 45. 3 times 25 is 75. 75 plus 45 is 120. Minus 120 is 0. And you can prove that neither of these are unit vectors as well. If we take the norm of the projection of B onto B, we got the square root of negative 6 over 14 squared, 9 over 14 squared, and 3 over 14 squared. (36 plus 81 plus 9 over 196. This is 90 plus 36. Square root of 126 over 196 is not 1. So this is not a unit vector. And you can do the same thing with this one and find out that it's not a unit vector as well. I can see right away 20 squared is 400. We're already over 196. And you add the other two, you're just getting higher. So that'll wrap up this chapter, or not this chapter, this section of this chapter. 11.3 is done. 11.4 is next. It's on cross products. Peace out, baby.